So I did want to go through properties of definite integrals here. So there are kind of 7 main properties that we deal with. We're going to have a few more that pop up as we go deeper into the material, but these are our main ones. And I'm going to go pretty quickly through most of these because a lot of them are very similar to ones we've seen already with derivatives and with limits, because definite integrals are a type of limit. Some notable ones, though, are, for example, the order of integration. The order of integration says that the integral from a to b of f of x with respect to x is equal to the negative integral from b to a. The idea of this would be if I were to draw a number line and say, here's a, here's b, the normal way of approaching it is I'm saying I'm starting at a and I'm going to b. But if I said, well, what if I want to go backwards? Going from b to a is the opposite of that. So that's where the negative is coming from. The negative one is saying I change my directions. Instead of going from A to B, I'm changing directions to go from B to A. So I need the negative sign to change that direction. So that means that in the example here, the integral from 5 to 2, and this is where we would normally use it, we don't typically say I want to go from a large number to a smaller one. I want to change the direction, so I'm going left to right like I'm used to. That's going to be the negative of the integral from 2 to 5 of x with respect to x. The zero property is one of my favorite ones because it's really quick if you notice it. It just says if my upper and lower bound are exactly the same, my definite integral has to be 0. And this makes sense because if my upper and lower bounds are the same, that means the width of my region is 0. So the width of every single rectangle is 0. And if the width of the rectangles are 0, the areas are 0. So they like to ask this on the AP exam with really complicated integrals. But if you pay attention that the lower and upper bounds are the same, it doesn't matter how complicated the integral is. It will automatically be 0. So here, the integral from 7 to 7 of 3x plus 1 with respect to x, because the upper and lower bound are both 7, automatically that's 0. There's no work to show. That's it. The constant multiple, this is just like the constant multiple rule with limits and with derivatives, because this is one based upon the fact that a definite integral is a limit. And it says if I have a constant multiple inside the integral, by the way, all of what we're taking the integral of is called the integrand. So if I have a constant multiple in the integrand, I can pull it out of the integral. So if I have the integral from 2 to 5 of 7x with respect to x, the 7 is a constant multiple, so I can pull it all the way out and say I'm dealing with 7 times the integral from 2 to 5 of x with respect to x. This tends to be one that we do kind of subconsciously without often explicitly showing that we're doing it, but there are times in which it is nice to show that I pulled the constant multiple out. The sum and difference, just like the sum and difference with limits, just like the sum and difference with derivatives, because this is based on being a limit. And it just says if I'm adding or subtracting in the integrand, I can split it up and do the integral of each piece and add, subtract all of those integrals. This is one that we almost always are thinking of subconsciously, much like the constant multiple. There are times in which we will want to be more explicit in saying we're doing this, but a lot of times it's just kind of automatic. So for example, the integral from 2 to 5 of x plus 4 with respect to x, I can split up and say, well, it's the integral from 2 to 5 of x with respect to x, plus the integral from 2 to 5 of 4 with respect to x. And by doing that, it gives me easier definite integrals to evaluate. Domination is just a fun one to talk about. This tends to be one that's done as one of the AP exams multiple choice, where it's a Roman numeral, like pick which of these, excuse me, pick which of these Roman numerals are true. So if f is always bigger than g, then the integral of f is always bigger than the integral of g. And what it basically means is it comes back to our areas. Because if f is always bigger, their rectangles are always taller. so the areas will have to be bigger. But to give a quick sketch of what this could look like, if f is x squared plus 4, so this would be f of x, and g of x is negative x to the 4th minus 7, and I say I'm going from 0 to 3, just looking at this, I can already see that, okay, yeah, f is above the x-axis, that's going to be positive, whereas g is below the x-axis and will be negative. So yeah, the integral from 0 to 3 of f of x with respect to x is going to be greater than or equal to the integral from 0 to 3 of g of x, because on that interval from 0 to 3, f of x is greater than or equal to g of x. And it's just that idea. If f is above g over the entire interval, then the integral of f has to be bigger. The max-min inequality, it allows us to do what's called bounding our integral. There are times in applications where we don't need to know the exact value of an integral. We just need to get a rough idea of what's it between. And the idea of this is, instead of using an infinite number of rectangles, we say, well, let's use just one rectangle. But instead of left or LRAM or RRAM, it says, let's use one rectangle where the height is the minimum of the function, and one rectangle where its height is the maximum. And my function's actual, or the definite integral's actual value will have to be somewhere in between those. So if I were to look at the function sine of x from 0 to pi over 2, so if I say f of x is equal to sine of x, and I'm looking from 0 to pi over 2, I don't need to know exactly what this definite integral evaluates to. I just want to know what's it between. Well, I have two options for rectangles. Either option, the width is going to be pi minus 2 minus 0, which is pi over 2, not pi minus 2, pi over 2 minus 0. But then for my height, one option is to use the minimum value of f in that region, which would be 0. The other would be to use the maximum value of f, which would be 1. So that's my maximum for f. And the 0 was my minimum for f. So the smallest possible value for my definite integral would be using the smallest rectangle, which would have a height of 0 and a width of pi over 2. And the largest would be if my rectangle had a height of 1, the maximum for f, times a width of pi over 2. So that definite integral has a value somewhere between 0 and pi over 2. The additivity, I'm actually going to save this one for a separate video because it's going to take me more time to talk about additivity.